Okay, so today we are starting Wiener filtering. Wiener filtering. So let me explain the setup. Let's say that I have in my hand a process X of n. So this is the observed process. And there's a second process, D of n. Let's say this is the desired process. And I know that these two processes are jointly white and stationary. Now the question is, I want to estimate the desired process from this observed process using a filter. So let me draw this. This is my X of n. Let me write this better then. X of n. So here is my filter. This is W of C. It is producing an estimate of this desired process's end sample. Okay? So let's say that hypothetically I have this desired process over here and plus minus, this is my E of n, error at time n. And the goal is I would like to design this filter such that the goal is to design W of C, so this is an LTI filter, such that expected value of D of n minus this estimate, parentheses square, what we call this error process, you may say, is minimized. Okay? That is our task. So this expectation is obviously over this, this desired process, let's say D of n and X of n, isn't it? But since this filter is, let me erase this. So I should define this filter. So this is, let me write it like this. This is like over X process and D process, okay? Since they are jointly white and stationary, I should be able to calculate this expectation, isn't it, from that information. So I'll be having correlations, etc. I should be able to handle that. So the goal is how you design such a filter for the estimation of the end sample, let's say. Okay. So case number one. So this is FIR Wiener filter. So I'm assuming that my W of C is in this form. W0 plus W1 Z inverse. And I have P taps, okay? So number of the coefficient is P, from W0 to up to WP minus 1. So this is the transfer function of this filter. Clearly this is an FIR filter. And if I sketch this impulse response of this filter, W of n, so I get W0, W1, maybe this is negative, W2. Let me write this one like this. W0. This goes like this up to, let's say, W P minus 1. And the rest of those samples are equal to 0 in the impulse response. And since this is a causal sequence, okay, causal impulse response, so I have basically P taps over here. P filter coefficients, mainly I can have P coefficients. So what can I do about this? So of course I can do the following. Method number one. Well, I can write this D hat of n. D hat of n is nothing but convolution of x with this W of n. Okay? So let me write this. K is equal to 0 to P minus 1 x of n minus k. Okay, this is the convolution result. Then I can write this. So this is my cost function. So this is my w vector, vector of unknowns. So the expectation will be d minus d hat, isn't it? D of n minus w of k, x of n minus k, parentheses square. And I can say that then I will be taking derivatives with respect to w0, w1, or derivative with respect to this gradient with respect to this w vector and equate it to 0. Okay, so I can do this. Equate this to the 0 vector and get optimal coefficient, let's say, equation. Of course I can do this. It won't be a big trouble, because if I take the derivative of this one, let's say with respect to w, let's say L, then derivative of this with respect to WL, derivative will be inside of this expectation. Then 2 times this error times inside of this error derivative with respect to WL. So you get error times x n minus L with a minus sign. Okay. Of course I can do that, but I have done similar things, in our linear MMSE estimation many more times. So I don't want to repeat it again and again. So instead of doing that, I would like to use my vector notation. So let me define the following: W0, W1 up to WP minus 1, and I have x of n minus 1. So as you see, I'm switching to vector notation. Okay? So this and that, they're exactly the same. W0 times xn, W1 times xn minus 1, and so on. Okay, so let me call this vector, obviously, W transpose. So let me call this vector x of n. Of course, there is some ambiguity, because this is all the samples of x of n in the history, okay, of x of n, let's say last p samples, including x of n. So let me write it like this: last, let's say, p samples of x of n, starting, including, or let's say starting from x of n to the last one is this, x of n minus p minus 1. Okay, that is it. Okay, so this is my notation. So let me erase this part then. And express this error in terms of something that we know. Okay, so let me again write this. Then J with respect to this W, this thing, is equal to expected value of D of n minus W transpose of x. This is parentheses square this. Okay. Well, if I call this y, for now, let's say that I'm only estimating this and dn. If I call this y, so how about this one? Y is a random variable. This random processes n sample. Obviously, this is a random variable. How about this x of n? These are bunch of random variables. So the question is estimation of y given this x vector. Am I right? So in terms of a linear estimator, and this is nothing but our linear MMSE problem. So this is our familiar linear minimum mean square error problem. Okay. So what is the solution of this? Well, we have practiced this many times. So this is R, X, and Y. That is the solution. I know about that. So let me try to find this Rx. And if I can find Rx and Rxy, I am done. Okay. So again, so my goal is estimating d of n, as you see. So I'm calling this as y and writing this equation, because that's the same as a generic linear MMSE problem. So what is Rx? So let me write my Rx matrix. So this is my Rx, which is equal to expected value of x of n minus 1, n minus p minus 1, times x of n minus 1, n minus p minus 1. Okay, maybe I should make this matrix a little bigger. So this part is x of n minus 1, and the last element is p minus 1. So let me write this vector over here, just to see these terms. Okay? So this is my Rx matrix. So what do I mean by that? So I should take this times that, basically xn square, and take its expected value. So what do we call this? Well, this is supposed to be, let me focus on this term. This is supposed to be expected value of xn times xn. Am I right? Because that is this term, which is, in general, Rx n, n. Autocorrelation of this xn process, n, n. But since this is White-Sand stationary, this is, I know that it's Rx0. Okay. There is some abuse of notation, as we have said. This is 2 argument, this is 1 argument. But I know that if the process is White-Sand stationary, this can be written as a function of a single argument. Okay. So this is, then let me write inside of this, Rx of 0. So how about this one? This is Rx of 1, and n minus 1. How about this one? This is Rx of p minus 1. Okay. So first argument is n, second argument is this, argument 1 minus argument 2 is the argument of the autocorrelation. Okay, that is it. How about this one? Now I have Rx of minus 1, Rx of 0, so Rx of p minus 2. Okay, because I am decrementing by, instead of 0 I have minus 1 over here. Okay, I have that one. So this goes like this, Rx of minus 2, Rx of minus 1, Rx of p minus 3, and at the end I have Rx of 0. So this is a p by p matrix, am I right? This has p over here. So this is Rx of then minus, okay, this is a little p minus 1. Okay. Then this is Rx of minus p minus 2, goes like this. So this is a p by p matrix that we write from this, autocorrelation information of this xn process. Very good. Now how about this w? W is the unknown vector, no problems with that. Now how about the other one? Let me write this one. So this is Rxy. So this is expected value of, well, this is this vector, xn minus 1, xn minus p minus 1. Because this has only p taps, this is a p by 1 vector times y. But what is our y? Y is d of n. So let me write d of n immediately for this. But clearly, this is y. Okay, over here. As you see, I'm not using conjugates. So let me make a note of this. So for the rest of the course, we focus on real valued processes. So don't worry about conjugates, okay? So for the rest of this course, this is 36, lecture number 36. For the rest, why am I doing this? Basically, there is a minor notation difference in Hayes's textbook and this notation. This notation is a little bit more healthy, in my opinion. So that notation difference becomes important for complex valued processes. As you can imagine, that notation difference is important only for that. And if you focus on real valued processes, you can use this notation or the Hayes's notation, textbook notation. They are the same for the real valued case. So this is the reason that I don't want to confuse you any further with two different notations between this and textbook notation. And that is it. So if I briefly say what is different in Hayes, for the, maybe you can remember, we have defined the complex valued case like this. This is our lecture definition. Y hat is defined as X, okay? So this is our definition, let's say, our definition. And Hayes's definition is W transpose times X. This is definition in the textbook. So because of this, well, there is, whatever we write over here, Hayes writes the conjugate of this equation, because as you see there is over here Hermitian. In the textbook there is transpose. This can be an issue in the complex case, but writing this Hermitian is more beneficial for the other, it's more compatible with the other textbooks and so on. So I prefer this one. But for the real valued case, obviously nothing, coefficients are real, X is real, Y is real, and there are no problems. So for the real valued case, we have compatibility. Okay. So this is the reason that I'm not writing these conjugates around. Okay. Just not to confuse you. So how about this? Then this is equal to. So if I move this just to be compatible with Hayes, let me move it over here. If I write dx of 0 or dx of 1 and r dx of p. Okay? That is it, just to be compatible with this Hayes notation. Okay? So of course this is, for example, this one is also equal to r xt of minus p. Okay? xt of minus p. So if you multiply it like this is the first one and this is the second one, assume that you have a conjugate over here, then xt of minus, if you have a conjugate over here, that is that one. For the real valued case, d should be over here or over there. It can be either first argument or the second argument, doesn't matter. Okay? So, sorry, is this 0, p minus 1, sorry, I made a mistake. This is p minus 1, and this is then, let me write it one more time then. Minus p minus 1. Okay, this is also equal to this for the real valued case. This times that. Okay. Then are we done? So if I know X's autocorrelation sequence, if I know their cross-correlation sequence, but they are jointly Weissan stationary, I am done. Now here is the case. Well, in this equation system, do you see a dependency on n? Well, this n. So in this matrix, for example, do you see any n? Well, I see Rx0, Rx1, etc. So there are no n's. Over here, do you see any n? So what we see is that the filter coefficient is because of Weissan stationarity, essentially, because this difference does not depend on exactly. So similarly, this only, it does not depend on n, it depends on the difference of these two arguments. So what we see is that, this optimal filter coefficients does not change by, or linear combination coefficients W does not change by n. Okay? So, for example, if I want to estimate dn plus 1, okay? So let me write this like x of n. This is x of n vector. If I want to estimate dn plus 1 from xn plus 1 vector, I get exactly the same optimal coefficients. Okay? Because if I shift this by one sample to the right or to the left, this correlation matrix and this matrix does not depend on that. So instead of defining y as dn, if I define as n plus 1, I get the same, exactly the same equation system. Okay? Then, by solving, Rx is equal to W is equal to, let me write it like this, Rdx. Okay? We get optimal filter coefficients for FIR case. Okay? Obviously, this is a P by P matrix. Okay? This is a P by 1 vector, and so on. So can I calculate the error? Well, again, I can use my linear MMSE results and get the error also. So let's say the value for the MSE value, let's say, for optimal filtering. So what's MSE? MSE is expected value of dn minus this parentheses square, but for which? When W vector is Rx inverse Rdx, okay? For this optimal W, okay? So how can I get this one? Well, let's do this one more time. This is like error. So this is E of n times, one more time, E of n minus W transpose. This is E of n times this vector. Okay? So by orthogonality principle, so what is this? This is the estimation error. Well, this is y minus y hat, as we have said, for the nth sample. I'm trying to estimate the nth sample, but as I have said, estimation of the n plus first sample is also the same. So actually, this is like a generic n. So by this orthogonality principle of linear MMSE estimators, error is orthogonal to the observations, as you see, for the optimal estimator. So I'm end up with this. Then let me also write this. Then I have dn parentheses square minus W transpose expected value of dn xn. So this is Rd0 minus this optimal filter coefficients times Rdx. Okay. So if I write this from this one, this is Rd0 minus Rdx transpose Rx inverse Rdx. So this is linear minimum mean square error estimate for this. Okay. So that is the end. So let's have an example and let's try to apply this. Okay. So I think what we are trying to do is clear. So again, this is even a simpler problem than our earlier linear MMSE discussions, because it's just a simple linear combiner of, you know, n coefficients. Previously we have defined, you know, what? Nonlinear estimators. We have compared nonlinear estimator performance with the, let's say, cubic estimator and so on. This is rather standard actually. Okay? But this is very important from signal processing viewpoint, because this is nothing but, you know, the famous Wiener filtering. Okay? So what's our example? Now x of n, so this is our observation, So this is desired signal, obviously. This is noise. Now I know my desired signal is, sorry, let me write this. I know my autocorrelation of my desired signal is this. So, for example, if alpha is a large quantity, let's say 0.99, okay, so I can say that this remains. So what do I mean by 0.99? For when k is equal to 0, I get 1. Okay? For k is equal to 1, I get alpha. So I can see that this autocorrelation is something like this, decaying like that. Okay? So autocorrelation shows the linear dependence between the samples. So if I make it decay much slower, meaning that alpha is closer to, let's say, 1, then we see that my samples are more and more correlated as alpha gets closer to 1. Okay? So this is what I have. I see an exponential correlation. Actually, this is nothing but an AR1 system that we have previously studied. So this signal is assumed to be, if alpha is a positive quantity in between 0 and 1, something like that, then it's assumed to be correlated with neighboring samples. How many neighbors? It depends on alpha. Okay, I have a high correlated samples in the neighborhood of a sample. Okay. So about this, RV of k, sigma v squared delta k. This is even easier. This is what we call white noise, right? And I'm assuming that this is our typical assumption. These are uncorrelated, meaning that d of n and v of n uncorrelated. Okay. Of course, this is a very reasonable assumption because this is just like noise. So when I call something like noise, this has nothing to do with the desired signal. Okay. Maybe this is the electronic noise. Maybe this is something that you are trying to listen. Maybe this is like a radio receiver. This is like the electronic noise. Clearly, this does not carry any information about this desired signal. Okay. If this term carries some information about this desired signal, we explicitly say so. Okay. For example, this is like the delayed version of this. Maybe there is an echo over here of this dn. Okay. But then that part will be carrying information about the desired signal. But in general, when we say noise, you may assume that these two are uncorrelated or even independent. Okay. But uncorrelated is sufficient for the sake of doing this expectations, meaning moments. Okay, very good. So what is our goal? Let me look at the problem. Find. Now let's say that again I'm trying to estimate d of n. Well, what is this? W0, x of n, W1, xn minus 1. Estimator such that MSE is minimized. I think it's clear. MSE is, I'm trying to estimate the desired signal, is minimized. Also, this is an example from Hayes's textbook. I'm resolving it one more time. You can look it up from the textbook if you want. Okay, so how should I go on with the solution? Again, vector notation is our friend. W transpose times x of n. Well, I don't want to write it again and again, but 2 by 1. Maybe that's good enough. So if this is 2 by 1, this is 1 by 2. Okay, W vector and x vector, I think it's clear. If you just compare with this, I think it should be clear. Okay, then if I define like that, what was the equation? Let me write it over here. Rx times W should be equal to Rdx, isn't it? So I want to solve that. But what is Rx? Okay. Then to start this problem, I should calculate this autocorrelation and cross correlation. So let me try to do that one first. So what is Rx of k? So this is expected value of x of n minus k. Okay. So if I do this, expected value of d of n minus k plus expected value of v of n n minus k. I have 4 terms. So these are the auto terms, you may say. And there's a cross term, d times v. But all of them will be equal to 0. Again, you can assume that, well, sorry for not mentioning this, but this is always the case. So we assume that d of n and, let me write like this, expected value of d of n, expected value of v of n is equal to 0. Because as I have said, if I have some other mean values instead of 0, I can always add that information to the problem later on. It's not a big deal to deal with the mean values. So in practice, the mean is explicitly stated over here. Maybe you have a 5, 6, whatever. So if it's not stated, then you may assume that, if it's not stated in the problem, you may assume that these processes are 0 mean. Then the cross terms, since they're uncorrelated and 0 mean, meaning that dn times vn minus k, if I multiply dn by vn minus k, this is v, then this is the product of expected value of dn, expected value of vn minus k, and it's 0 times 0, it is this. So how about this one? This is rd of k, this is rv of k, but I'm already given that. Alpha to do this, sigma v square delta k, and I'm done. Let me write this better, square delta k. So about this, r dx of k. So this is expected value of d of n, x of n minus k. Well, again repeating this, this is d of n minus k plus v of n minus k. This times that gives you rd of k. This times that gives you another 0. Okay. So we are done. So after finding this, we are almost done. So I need to now write this matrix equation system, but I have full information right now to fill in the entries of this vector and matrix and vector. Okay. So how about this? This is again linear combiner xn minus 1, xn minus 1. So what do I mean by this? This is expected value of xn minus 1 times, let me write xn over here like this, xn minus 1. Okay. So again, I have Rx of 0, Rx of 1, Rx of, this is minus 1, but it's equal to Rx of 1, Rx of 0. Okay. So this is, well, let me use a different color then. W0, my W vector, W1. So how about this? Now this is expected value of Rdx. And we have studied this. This is Rd0, Rd1, because this is nothing but expected value of d of n times x of n. The second element is expected value of d of n times xn minus 1. Yes, okay. And this is Rdx0, Rdx1, Rdx0 is this. Okay. If you wish, let me put dx over here. Oh, sorry. Rd of 1 over here. Then let me write with this. Rd of 0, Rd of 1. Okay. So what are the values of this? Well, if I write the numerical values, so this is when k is equal to 0. Let me write this is equal to 1 plus sigma v square. Okay. This part is when k is equal to 1. I think it's alpha. Okay, just to see it. This is also alpha. This is 1 plus sigma v square. This is alpha. This is, no, this is not alpha. This is equal to 1. RD0, where is it, is equal to 1 and alpha. Okay. So I have such an equation system. So this is the end of the problem, just for exercise. Okay. So just for exercise, numerical exercise, let's set, let me make sure of these numerical values. Where is that note? Alpha is equal to 0.8 and sigma v square is equal to 1. Okay. So if I do that, one plus this, I have 2 alpha 0.8, I have 1 and 0.8 over here. So if I solve for this optimal coefficients, W0 is equal to 0.4048, W1 is equal to 0.2381. Okay, so I get some numerical values. Okay, so can I calculate, let me use this, and let's calculate the linear MMSE error. Okay, we are done. So I can right now define this filter as two-tap filter, 0.4048 and 0.2381. So this is my impulse response for this two-tap filter, as you see, causal FIR two-tap filter. Okay. As I have said, you know, this filter is a constant filter. So using previous two samples, it is predicting the D of n from this observation, getting rid of this noise, in an optimal way. Okay. For every sample, it's capable of doing that. The reason is this linear combiner doesn't change. If you know this, if you combine, let's say you have a process like this. This is the observations of X. Now you are combining these two by these weights, and you get a result. Okay. So this is, let's say, 0, 1, 2. So X2 times this, X1 times this, you get an estimate for at time 2. Okay. Now you move to this one. So this is the third, this is the second sample. If you do the same operation for the third sample, meaning that third sample is multiplied by that, convolution operation, second sample is multiplied by that, you get a second estimate, but this is for the third sample of this desired sequence. Okay. This is a convolution operation. So optimal filter is the same filter for this linear MMSE estimation problem and the other MMSE estimation problem. The reason is Weissen's stationarity. If you write this because the difference of these samples play a role. Okay. That is it. So let me calculate two-tap linear minimum mean square error. So what is this one? So I want to use this. RD0 from, okay, let me write this in case. So this RD0 minus, well, let me write it, RDX. So what is RD0? It is 1 minus, how about this RDX? RDX is right hand side, right? It's always this right hand side vector. 1 alpha, well, alpha, okay, but let me write the numerical value, 0.8, and this is equal to the unknown vector, isn't it? This part is the unknown vector. So this is equal to 0.4048, 0. This. Okay. And my final result will be, okay, for this one tap filter. we see this is again 0.4048. Okay. Okay. So this is the end of the problem, but also let's do this. Let's also compute one-tap Wiener filter and calculate its MSE, and compare with this. Okay, but one-tap filter. So what's a one-tap filter? D of n is equal to, well, this is, let me call this a different notation. Let's say gamma 0 times x of n. Okay, one-tap filter. And of course, I am setting gamma such that, the Wiener filtering cost function, this estimate, is minimized. Okay, that is it. So again, Rx times the unknown vector, okay, let me write this, times Rdx. But of course, this is one-dimensional vector, this is also one-dimensional, so I have only, xn times xn over here. So if I write this equation, I have Rx0, because this is xn times xn right now. Okay, and this is equal to dx, dn times xn, okay, is equal to gamma, is equal to Rdx0, okay, for this one-dimensional case. And we have calculated Rx, this is 1 plus sigma v square, gamma is equal to Rdx is alpha to the power Rd0, so this is just 1, okay. So gamma is equal to 1 over 1 plus sigma v square, and since in this problem alpha is equal to 0.8 and sigma v square is equal to 1, this is just 1/2, okay. So I get the optimal coefficient as 1/2. Then, so one tap, I'm trying to calculate this one right now, linear MMSE, okay. So again, Rd0 minus this times Rdx, okay. So if I do this, this is 1, my coefficient is 1/2, Rdx is right hand side of this, it is 1/2, so I get 1/2, okay. So error is 1/2. So if you compare with this one, oh, okay, doing a two-tap filtering actually improves the error. The error is smaller, okay. Very good. So the conclusion is, if I implement, maybe you are designing a system and you are trying to understand whether it works to implement, two-tap filter, because this is like double computation and so on, okay. Then you can say that, of course, if this reduction of the error in terms of mean square error is important for you, then implement two-tap filter. Now the next question is, how about 50-tap filter, 60-tap filter, and so on, okay. So where should I stop? What is the limit of this? Later we will calculate infinite impulse response filters, IIR filters, and you can get a number for the IIR filter. So in practice, if you are very close in terms of linear MMSE to the performance of an IIR filter, infinite impulse response filter, then you stop, isn't it? Because it doesn't worth any more computation. Okay. So that is it. Okay. So this is the end of this example. But let me also do this. Let's also, too many let's. Let's set, let's compute. Let's also discuss SNR before and after, let's say, noise removal from observations by Wiener filtering. Okay, so I think it's clear what we mean by noise removal. Remember, X of n is nothing but noise version of desired process, D of n. So I get reduced, as you see, error with these estimators. So D hat of n is a better representation of D of n than X of n, obviously. Okay, I'm reducing the estimation error. So how about SNR? Okay, but to do that, let me discuss this. What is the SNR definition? D of n plus D of n. So for the SNR definition, please remember, there is a signal term. Actually, this is a very rough definition. This is a noise term. There can be several other definitions like this, but this turns out to be coming up in many, let's say, optimal design, let's say, estimators or some other optimization problems. This ratio comes up, the ratio that I will calculate. Okay. So SNR input is defined as this: expected value of whatever you have as signal, you take its square and take its average. Again, this makes a lot of sense from the electrical engineering viewpoint, because this is like an average power operation. Assume that you are measuring voltages, okay, V, then V square over R is nothing but the power, okay, power dissipated over a resistor. R is resistance. So if resistance is 1, you can say that this is the power dissipated over a resistor of 1 ohms, but on the average. Okay, so in AC circuits, for example, you have this averaging operation over, let's say, many cycles. Okay, so that's called average power. Now I'm calculating this average power dissipated over 1 ohm resistor over the ensemble of signals. Okay, so it's like an ensemble average, but again, it's like an average. This tells me what is the average power. The concept related with energy of the signal. Okay, this is very critical. So this is the ratio of those two, SNR input. So for our case, well, D of signal is D of n. So D of n square. So by definition, this is RD0. Because this is D of n square after expectation RD0. So this is RV0. Okay. And in our case, this is alpha to the power k. When k is equal to 0, this is 1. Okay. This is sigma v square delta k when k is equal to 0. That's also k is equal to 0 and sigma v square is equal to 1 in our numerical example. Okay. So 1. Okay. So we say that SNR is equal to 1. Noise power is equal to the signal power. So let me also write the following. Sometimes we write SNR in dB. Okay. So SNR in dB is as follows. You take logarithm of this in base 10 of SNR in linear scale. Okay. So this is again the same as dB scale for let's say AC circuits. You may remember, for example, if you are sketching frequency response in dB, you should be a little careful whether this is 20 or 10 or etc. But what's the reasoning behind this? This dB scale is considered as dissipated power from the viewpoint of dissipated power, and as you see, at least the numerator part is this is related with the power. That is the reason that I have 10 over here, because it's like V square. Okay, so V square. If you 20 log 10 of V, then this will be 20 log 10 of V will be the power. But since it's already V square over here, I'm already taking the second power, so I don't need to have 20 over here. I need 10 because this is the power argument. Okay, that is it. SNR dB definition. So it can be a little, more intuitive. This corresponds to 0 dB. Okay, So once you get used to thinking in terms of dBs, it can be a little bit more, let's say, helpful in many calculations. Okay. So this is 0 dB. Okay, so let me then do a one-tap filter. One-tap filter study. So what was our one-tap filter? D head of n is equal to, I think this was gamma x of n, and gamma was 1/2. Am I right? So this is, well, let me write gamma again. Gamma is something like this. Then this is equal to gamma d of, this is gamma d of n, plus gamma v of n, because x of n is this. So what is the signal term? Signal is scaled by gamma, and noise is scaled by gamma at the output. So what do you see? SNR at the output of, let's say, one-tap filter. So this is my, signal, new signal, output of that filter, isn't it? Please remember, this comes in, there is a filter W of C, this is producing the head of n, so this is supposed to be better than the input in terms of, mean square error and so on, okay? So how about the SNR? So we see that, well, nothing changes, because this is expected value of gamma square dn square divided by expected value of gamma square vn square, okay? Because square of this, and this cancels, so I get 1, okay? So this is somewhat obvious, because if I scale desired signal by a factor and noise by a factor, so their power is scaled by their, this factor's second power, square of that, and if the ratio is calculated, there's a cancellation, okay? So again, I see 0 dB, no improvement. So let me write with this. No improvement in SNR. So actually this is a little bit disappointing, but what can we do? Because we are implementing such a simple, one-tap filter. So how about two-tap filter? So what is d of n? Well, these are, I guess, 0.4048, and 2381. Let me erase this. Times. So I'm writing in vector notation. So this is x of n minus 1. Am I right? This is our convolution structure. This times that, previous sample is multiplied by this. Here is the impulse response. That is it. So where is the signal term and where is the noise term? Well, okay. Then let me write this like x of n with this obvious notation, d of n plus v of n. Okay. So let me also call this w, let's say 2-tap. Of course, transpose of this. Okay. Then W2-tap, this is transpose times desired vector. So what do I mean by last two samples of this? Desired dn minus 1 is written over here as dn vector, obviously, for this equality to be meaningful, plus W2-tap transpose this thing times v of n. Well, I will call this thing as my signal because it contains all of these d terms. This is my output noise. Okay, I have that. So can I calculate the power of this? This is a scalar actually, isn't it? This is just a scalar because this is, output at the end time of that filter. So I should be able to calculate second power of that scalar and take its expected value. Then SNR at the output 2 tap. So this is signal power. So expected value of W2 tap D of n and second power, oh there's a transpose. Then let me write it like this. This is the transpose of this. Let me move this, okay. Transpose over here times this. And let me write the same thing for the denominator. This is vector, vector. Okay. So if this is my, let's say S, signal is, let's say S, okay. This is also S, because it's just a scalar and it's transpose of that scalar. Okay. We have done similar things before. This is, let's say, noises, let's say WV, let's say noise is beta, something like this. If this is beta, this is like beta transpose, which is equal to beta. So this is beta square. Is this clear? These are just numerical values. It's just a scalar. Okay. So I'm taking the square of that scalar quantity. I have that. So why am I doing this? Now I can take these W2 tap out, and I have RD over here. This times that. W2 tap divided by W2 tap RV W2 tap. Okay, that is it. So are we done? I think we are done, because I know this matrix. This is 1, 0.8, 0.8 and 1. This is equal to 4048 2381. This is equal to, in our case, 1. Okay, so I can calculate this ratio. So if I calculate this, I get SNR of, I can find it over here, SNR around 2 dB, well, which is good news. So if I do this calculation, so it's an improvement from 0 dB, as you see. For 2-tap filter, I see an improvement of 2 dB. Very good, I am happy. But here's a question. Can I do better? Okay. So what is the best SNR at the output after 2-tap filtering for this problem? Okay. So can I find that? So here's a question. What is the maximum SNR for this problem with a 2-tap filter? So how can I answer this? Okay. Now, so the issue is, assume that this is left as a optimization variable, W2 tap. So how can I maximize this ratio? So let me write that problem. W max SNR is then equal to, this is the argument in terms of W. So I'm looking for a linear combination vector such that W transpose RD W transpose, but this identity is maximum. Okay, so I want to maximize this. So I know that if I have this as my W vector, result is almost like 2 dB, approximately 2 dB. But is it the best? Can I what is the maximum of this function? Okay. Now one thing that we can observe is, this denominator is this. Okay. I have things like that. So again, if I, for example, can I write the following? Assume that there is an optimal W, this W max SNR, a vector is known. Okay. Then you insert that vector in this, then you get a value, you get, let's say, 5. Okay. Then output SNR will be 5. You include this W vector over here. Now here's the issue. If you multiply any W vector by a scalar, let's say by gamma, then the numerator is multiplied by gamma square, denominator is multiplied by gamma square. Again, those gamma squares cancel. So you see that this vector cannot be defined uniquely. Actually, that's what we have seen in one-tap filtering. Because if I multiply, this prediction result, let's say, by an arbitrary gamma factor, SNR doesn't change. So I can, filter with a weight and then multiply by gamma, SNR doesn't change. Okay, so that means that I'm multiplying the filter coefficients by gamma, and SNR obviously doesn't change. We can see it from there. Now from this observation, I can also say that, okay, then I can write the following: arc max. I'm maximizing over this omega, but under this condition. Let's assume that my omegas are, sorry, not omega, my W's are unit norm. Okay? Because I can always, given an optimal W, I can always scale it to unit norm. Okay? I can always do that. So there is no loss with this assumption. Okay? Assuming that there is an optimal, there is an optimal solution to this problem. Then, very good, I have 1 over here. Then this is W transpose RD W. Okay? So how can I, maximize this? Okay? So maximizing W transpose RDW. Maximizing this. So let's think about this a little bit. Okay? So what can I do about this one? So let's see. If I say that, let's try an eigenvector. An eigenvector of RD. For example, RD is equal to E1 times, let's say lambda 1, the first one, let's say, E1. Okay. So first of all, I'm sure that there will be, if this is an n by n matrix, n eigenvectors, because it's symmetric, all of them are orthogonal, and there are n of them, spanning the whole space. So I can find these eigenvectors, and they will be forming an orthogonal set. So if I set this as this, so what do I get? W transpose RD W. What do I get? I get over here so I get W transpose times lambda 1 E1 because of this, this is an eigenvector, this part. But this is unit norm. Okay, let me normalize my eigenvectors because this has to be satisfied, isn't it? Let me normalize them to unit norm. I don't even need this second power over here. So this is then lambda 1. Let me write this a little bigger. This. So I get lambda 1. Okay. So how about this? Can I, if I have two eigenvectors, so let's say that W is a combination of two eigenvectors. Okay. So just we have tried the first one. Let's assume WS, a combination is a combination of two eigenvectors. Okay, so what do I mean by that? WS, let's say this is alpha times E1 plus beta times E2. Combination of two eigenvectors, well, E1 or E2. Okay, both of them satisfy this with lambda 1 and lambda 2. But please remember that I have to satisfy this condition. In order to satisfy that, so what do I have? Well, you can easily see this. This is like alpha square plus beta square should be equal to 1. Okay? Why? Because if you include it over here, you have these cross terms of E1 and E2. Those cross terms are E1 transpose times E2. They're equal to 0 in this product. There are 4 terms. And there is E1 transpose E1 also. But I have assumed that these are, orthonormal sets. So this is 1, so I get alpha square beta square should be equal to 1. Okay. So then I see the following. If this is alpha, then beta is something like this, 1 minus alpha square E2. It has to be like that. So let's give this one a try over here. So let's try, let's say this as the W vector. So what do I mean by that? So I need to check this, maximization, the objective function for this vector. So W transpose RDW for W is equal to alpha E1 plus 1 minus alpha square E2. Okay. Well, now this is unit norm. We have discussed that. So let me try to calculate this objective. So what do I have? Again, you have alpha square. Well, because of this, you have lambda 1 plus you have 1 minus alpha square lambda 2. Would you agree with that? Because if you process this part like this, you get this. So this part means, since both of them are eigenvectors, I'm multiplying this W by this part by lambda 1, this part by lambda 2. Okay? How about this? Then if I do this W transpose calculation, so there is a lambda 1, lambda 2 over there, and again I'm multiplying by the same thing, so this is the reason that I have alpha squares. This square root goes away. Again, cross terms are equal to 0 because E1 is orthogonal to E2, so I get something like that. Now here's the observation. Now this is summing to 1, isn't it? So this is like weighted average of lambda 1 and lambda 2. So this is weighted average of lambda 1 and lambda 2. What do I mean by lambda 1 and lambda 2 weighted average? For example, if alpha square is 1/2, this is like the arithmetic average. Okay. Well, because lambda 1 over 2 plus lambda 1 over 2. If lambda square is 90, this is then 90%, this is like 10%. Okay, so it's like always like the weighted average. So clearly we see that this is smaller than, well, the maximum, whatever the maximum of this, lambda 1 or lambda 2. Okay. Well, because this is the weighted average. Average always smaller than, this is the average function. Average function output is always smaller than the maxima, and it's greater than the minima, isn't it? So this is the case. So what's the conclusion? So I see that conclusion. So the eigenvector of RD with maximum eigenvalue is the SNR maximizing solution or filter coefficient. So what do I mean by that? Let's say that RD has eigenvectors in this form. There is lambda 1, again lambda 2, lambda 3. So these are all real numbers because RD is a symmetric. So these are the eigenvalues and these are the corresponding eigenvectors. Okay, E1, E2, En. Now, I claim that this is the maximum, lambda max. Maximum eigenvalue. Okay. Now, I claim that if I use this E1 as my solution over here, I get, according to this, E1 is lambda max, maximum. So, if I include any other eigenvector from here, let's say by this ratio, 90%, 60%, any other of them, so I get, something less than lambda 1. Lambda max. So I should be using this. Okay. So if we return back to our original problem, what was RD? 1, 0.8, 0.8, and 1. Okay. Since this is a symmetric matrix, and it's a 2 by 2 symmetric matrix, so I can write eigenvectors of this. Maybe I should erase this because I want to write it over here. Let me write RD over here. So here is the first eigenvector, 1, 1. And this has lambda 1, 1.8. If you don't believe me, just apply. RD times 1, 1 is 1.8, 1.8. So it's a vector of 1.8 and 1.8. So its lambda 1 is 1.8. So the other eigenvector is 1 and minus 1. This is specific for, 2 by 2 symmetric matrices essentially, 1 and minus 1. So if you do this, I have 0.2 minus 0.2 over here. If you multiply this matrix by 1 and minus 1. 0.2 on the first element, minus 0.2 on the second element. Then you say that second eigenvalue is 0.2. So then I should use this one. Okay. Then answer of this problem then SNR maximizing two-tap filter is 1-1 filter, meaning that W0 is equal to 1, W1 is equal to also 1. Okay? And the maximum SNR is max SNR output is equal to, so I can calculate this of course, 1, 1, but I know that this will be equal to, I should be a little bit, careful, 1, 1, 0.8, 0.8, 1, 1, and this is 1, 1, okay. So I get what? So I'm summing up all of these entries. 2, this is, let me write 2 times 1.8, or let me write 3.6, it's more confusing. 3.6 divided by 2, this is 1.8, and this is lambda 1. Okay, lambda 1. Well, since this is not normalized, so any eigenvector is, if I written this like 1 over square root of 2 over here, then this is orthogonal, and with this factor, now it is orthonormal, okay, 1 over square root of 2. Then I won't be needing this part, because calculation of this upper part will be enough, as we have discussed that part. So how many dBs is this? 1.8. This is like 2.55. Oh, okay, very nice. I can get 2.55. So previously I was able to get around 2 dB. Now I have better result. So 2.55 dB. Okay. So what we have seen? So we have seen today FIR Wiener filtering. So Wiener filter reduces the impact of noise on the observations. So it's like a noise removal filter in this application. Okay. But what we see is reduction of the noise or the improvement in the, let's say, signal quality can be an important measure. But if your measure is something else like SNR, then you should be a little bit careful. Okay. Now you see that MSE minimizing filter, the Wiener filter, does not maximize SNR. It does not necessarily maximize this SNR. Of course, it is helping in improvement of the SNR, but there can be a better filter. This is what we have seen. Okay. So 1-1 filter is better than Wiener filter in terms of SNR maximization. So we should be careful in the application of optimal filters. If a filter is optimal in one sense, it may not be optimal in another sense. Okay, we will continue with more discussions on filters later on. Thank you very much.